Hello everyone, it's March 24th, but we enter in tomorrow's territory. Let's see, two-city scheduling. Oopsie doozy, that's not the one. I haven't opened it yet. I was hoping that we can do this one today, finally. I think I opened it up, anyway, on Monday? Maybe on last Sunday. It's a long time ago, I didn't do it. Two-city scheduling. What does that mean? Schedule for two cities? Okay, company is planning to interview 2N people. Given the array costs, costs I equal to cost of flying the ith person to city A is cost this, and the cost of flying the ith person to city B is this. Minimum cost to fly every person to a city such that exactly n people arrive in each city. Okay. The minimum cost to fly every person to a city such that exactly n people arrive in each city. Okay. So the first person goes to A, second person goes to A, third person goes to P, fourth person goes to P. I see. I see what is going. Two times n equals costs dot length. Costs dot length is even, yes, because I have 2n people. And then each person go to 1. Alright, so what you want to do is to minimize the cost. So like at most 50 people, right? At most 50. Not really. I have 1, 2, 3, 4, 4 people. 2n people. Why is it 2n people? Oh, to emphasize it's an even number. Wait, does that matter? The same number goes to each city. It doesn't matter. So it has to be even number. Okay. So every person either go to one or go to the other. So try to do that. So which means if we have 50, no, not 50, we have 100. And then has to be even number of ones, even number of, no, it's the same number of ones, same number of zeros. A lot of different ways to do this. make it smallest. It doesn't seem to be DP to me because, well, if we want to try to think of this in terms of DP, like, no, it's not DP because you see these are 4, right? And then the optimal is this, and this. If we remove these two, now we cannot just have odd number, okay? It doesn't work. So I have to even, so remove these two. Just look at these, and it will be different. So I'll pick this and 200 or 20 or 30. Definitely will pick 20 or 30, right? It'll be 50 and 30. So now I'm trying to think about maybe merging, divide and conquer. The merging, so we have the minimum cost on this and the minimum cost on this. And they're all balanced, so we can either just merge them, it'll be 20, 30, 50, and 30, right? But then we can also ask the question, what if I don't want to do this? And what do you mean by don't do this? Because it's balanced, right? It's the left and the right is balanced. The question is, what is the minimum if we unbalance it? How do we unbalance? We swap, right? Because the left is all balanced, so we have the same number going one, same number going the other. The right is also. So if I want to swap, like say we swap, we take away we swap the one of the left, and then we swap one of the right. How many different swaps do we have? And how do you want to swap? It's a good question. So in this case, 10, 20, 30, 200. That's the left, and then we pick as 20 and 30. On the right side is 450, 30 and 20, and then we're picking 50 and 30, right? Now they're gonna merge. So we say, okay, now we're gonna have to swap. How do we swap? Well, it has to be on the left hand side. If I pick the second, then on the right hand side, one of the second has to pick the first, right? And then we try to see if they can make it. So if we start from here, mind you, this is 100, okay? Cost length is 100. So if on the left hand side I say, okay, I want to try to, because 10 and 20, yeah, if I'm already picking a small one, then if I swap, it can actually become bigger, right? So we try not to do that. We try to swap so that we can make it smaller. So 10, 20, say, okay, what if I want to pick 10? And if I want to pick 10, then we need to, on the right side, pick the ones instead of the first one, instead of the second one, to pick the first one, right? So instead of the second one, we need to pick the first one. So in here, so I'm picking one more on the first one. So we need to pick a second one. No, right. So we gonna have two first, or have three first. So the first one. So we pick the second one, become the first one. So the first one becomes second one. So we'll look for every one. Any first one, we can move that to the second position and see if that reduces. And it does reduce. Now the question is, do we do this for everyone? Now in this case, why don't we just pick the smaller one to begin with? Hold on. If we pick the smaller one to begin with, and then we can record, right? How many? Okay, let's do this as an example. Okay, we have 259,770, 448, 54, 926, 667, 189, 840, 118, 577, and 496. That's what we start with, right? I'm gonna pick the smallest. Okay, so when we pick the smallest, we find out that only one in the front is one, and the other all on the second one. So we need to, let's say, among these, then we have to swap, right? We have to swap to the other side. So we're gonna pick one that after the swap, it give me the least amount. So among these, if we rank them, 184 is the smallest, right? Yeah, so first of all, okay, I see. Do this, right? And then we need to do one more. So look through which one is smallest. 448 is smallest. So let's have a swap here. 448. That doesn't make any sense. It should be the swap will cause the, because this is the smallest value, right? So every time swap, when you can generate a increase in amount, right? It's increase in amount. So increase in amount. So 448 minus 54. That one will increase 394. But if we do, let's say, 477, 577 minus 469, that one only increase 108. Right, because it's the base, and then we need the increase. So we want to find the smallest increase. So the smallest increase, is it 184 minus 139, the smallest increase? Yeah, it's the smallest increase. So it actually should be this one. So now we get 259 plus 184 plus 577 plus 54 plus 667 plus 118. We get 1859. That's correct. Now let's try the last one. Again, I have 515, 563, 411, 451, 713, 537, 709, 343, 819, 855, 779, 457, 60, 650, 359, 631, and 42. So I'm going to take the smallest, okay? Take the smallest for everyone. Oh, as long as the smallest, everyone, it works. Okay, so this is the idea. We pick the smallest of all, right? And then we know that's definitely the smallest possible. Then if it cannot cover the entire thing, then we need to swap something out, right? And every time we swap something out, we will add a value. Now the question is just to find the smallest, like for the swap, right? So what will be the efficient way? So we pick the smallest, find a sum, and we need to know which one we need to do the swap, right? Which one we need to do the swap. And it has to be someone need to swap, right? And then among those, I do the swap. Now the question is, this is still greedy. I think this is still greedy. Now the question is this definitely the best option? If we don't do this, right, which means somebody else have a swap, and we say that one can achieve the smallest. Yeah, let's say okay, some like the ones that has the minority. So like after we pick the values, we have some minority and some majority, right? So the majority needs to swap, and that's the current theory. We only swap the majority, and it's straightforward. Like when we swap the majority, we have to swap the ones with the minimum increase. So that's done. But now the question is, why don't we swap the minority? So let's say we swap the minority, all right, and then we also swap the majority, and then we get to the final result. Okay. And if we swap the minority, we have to swap more majority, but that's fine. So if we say that is the smallest, right, we can always swap it. So what we're saying is when you swap, so you increase this, and then you have to increase 2 times more. So you have to increase 3 times more. And in my other solution, we don't swap, we want to swap once. So you're saying one swap is more than those 3 swaps, but no, that's correct. That's greedy works. Okay. So now we just need to implement it, right? So what do we do? So we go through, right, and then we can I don't know, put in an array. Okay, we'll put in an array to call it 0 or 1. Which one do we find? Okay, so if we pick 0, I'll pick 1, pick 0, pick 1. And then once we're done, we can sum that value. And if that value is equal to half of the length, now if the value is this, if the value is half of the length, then we're done. We just return the smallest value. If not, if it's smaller, that means we have more 0 than 1s. So we go to all the zeros. So we sort, okay? We sort all the zeros, and then we pick the first, or we sort all the ones and pick. Okay, that seemed to be working. All right, so first things first, we're gonna do choices, right? That's gonna be 0 times len costs. And then basically say for cost 1, cost 0, cost 1 in costs, right? So if cost 0 is smaller than what? Could they be equal to? Maybe. Equal to is fine. It's okay. Then choices. Oh shoot! I'll have to have I. We need to achieve a lot of. I need to know the choices. And more than that, I need to know. Yeah, let's just do this. I need 2 pieces of information, so cannot just do. I will just put the rest equals 0, right? So if this choices I will equal to 0, right? And we can do this. Choices equal to 0 if this else 1 and rest plus equal to the minimum of the 2. C0 and C1, right? So this one I have the choice under 0. I'm going to say if sum choices is equal to well, I just say if it's larger than n len costs, right? It's larger than n divided by 2. So this means too many ones, right? Then we just need to iterate through. Which we say we should get. Okay, so it's basically for C in choices. If C is equal to 1, I C in enumerate choices. If C, right, because there's too many, if C, then what we can do is costs, right? Costs C, 0 minus costs C1, and we're going to take ABS, absolute value of this. Actually, I don't know. I don't need to because I know these are choose 1, so 0 is bigger. So we're going to do this, and we need to turn this into a list. And we just sorted this small to large, and after that we're going to take the first something, which is sum 1 choices, right? So 1 choices equal to sum choices. I would say if 1 choices is larger than this, right? And then we do blah blah blah, and then 1 choice is too much. So how many we need to reduce? It's just 1 choices minus n divided by 2. So 1 choose 5 should be 4, so we should get rid of 1, right? So and then this is going to be the sum of this. Sum of this give me a total difference that we need to add to the final, right? So we just say rest is going to be plus equal to this, right? If this one is smaller, right? If this one is too many zeros, so if it's smaller then we do this. That should be 1 minus 0. right? So it's one choices, and it should be if C, if not C, right? If not C, then when you turn that into 1, and after that into 1, and that because it's smaller, so it's going to be this minus this, right? And if n is equal to, then we don't have to change. Then we're going to return rest. Okay. Let's see. Time-wise, I think it's fine. Just correctness. As time-wise is only 100, so it'll be very fast. But correctness, yeah, I think it's correct. We did analysis. Greedy, definitely, I think it works. You use greedy because we tried dynamic programming. It's not really working dynamic programming because it can change. The state doesn't stay constant. Right, so like the future smallest does not depend on the previous smallest. That's why it doesn't work. Oh, the second one is not right. The second one, I did it. That was not right. It's actually going to be a one choice larger than this, right? So it's if C and I do this minus this, and I sorted it, and I do one choices. It's 1, 2, 3, 4, 5. It's 5 one choices, right? And 1, 2, 3, 4, 5. That's 6. So that's 3. I need to do 2. I need to change 2, and I did change 2. Hold on. This is interesting. First, make sure that, yeah, that's correct. And sorted this. Let's take a look at where we get. Sorted this. Oh, that is not correct. Ah, that's not C. That's I. This is I. What do you use C for? C is just for checking. Okay. There we go. Now this one passed. Okay, so now I'm going to try it again. Of course, they all pass. So we'll check here. Looks fine. Try it. That's a new problem. It passes. So again, I think this is greedy. This week is always about greedy. $1029. I think this is greedy again. So first of all, we choose the smallest cost, no matter what. After that, we check whether either choice is dominant. If both choices have equal numbers, have been chosen equal number of times, we can return the sum of all the smallest costs directly. Otherwise, we need to perform swaps. We start from the min total cost, and each swap needs to be performed on the dominant choices, and the swap must happen according to the order of the difference between two costs. Essentially, the difference is the amount of cost that will be added to the main cost. Thus, picking a smaller difference means adding less to the total cost. Therefore, sort the cost difference array of the dominant choices and add the first k differences to the total, where k is the difference between the dominance, right? Dominance and equal representation. Now the algorithm of picking the smallest difference for swapping is sound. The only the only the only part that requires proof is why we only swap on the dominant side. Well, suppose we swap on the non-dominant side. Right, if say we swap on the non-dominant side, then we need to swap twice on the dominant side to reach equilibrium. Suppose, right, if this maneuver yields, so let's say this maneuver yields a very low cost, then no, we have to do 3 swaps, right? We have to do 3 swaps. So we need to swap twice. So in total, there are 3 swaps. It is always possible to let's say we need to swap. Call it A, right? Then we need to swap twice on the dominant side to reach equilibrium. Call it B and C. Right, in total, there are 3 swaps, A, B, C. Now it is definitely cheaper to not perform A and only perform the smaller of B and C. Now, in this situation, there is only one swap and it costs less. Therefore, swapping only the dominant side is proven to be a better choice. Okay. This is O(n). This technically is O(n) log n. So we call it O(n) log n. But since the n is so small, it doesn't really matter. 54. All right, I'm going to take a look at discussion. It's a similar idea, but it's done differently. Okay, n people. Oh wow. Oh, this is easier to implement. So it's the same idea. It's the same idea, but I think the implementation is much nicer. Oh, it was labeled as an easy. I don't think so. Yeah, we've been doing greedy the entire. It's like the week of greedy, but I like this solution. Let's credit. All right, so we call this. Let's call this the greedy. No, not greedy. I know the greedy. So this is a better implementation, right? From, let's credit. Now the idea is similar, right? So I should say the idea is similar, but we simply pick choice 0 for everyone, right? And then we decide which n people needs to swap to choice 1, right? And this to sorry, which n people just and the criteria, right? The criteria to choose those n people, right, is to see is to find the most find the people with the highest, right, the highest refund, right, the highest refund when swapping to choice 1, right? Which means when they go choice 0, it costs more, which means if we do choice 1 minus choice 0, it will become a negative value. So more concretely, right? More concretely, the n people should be chosen by computing, right? Computing the cost difference of cost 1 minus cost 0 and find the n smallest of them. Okay, so how do we do this? We have the base, it shall be the sum of, let's say, for C in costs, everybody go to 0, right? And then for C0, C1 in costs, we're going to compute C1 minus C0, right? Because we go to C1, and then we leave C0, right? So for all of this, we can sort it, and we take the sum of the top n, which is cost divided by 2, right? And we just simply return this plus this. Wow, that turned into a one-liner. I did not expect to turn into a one-liner, man. Run code. Oh, see? That's why I need to run code. You'll find a problem like this. I think this one should be fine. Let's just submit it. There we go. Yep, it's good. It's very good. 52, the same thing. O and log n. 52 milliseconds. 65. I think people have posted one line. I can actually search. Gotta be people running one line, yeah. Oh, one line. I don't know. So we sort by this, and then this, and then the sum v. I divided by this. Oh, I see. I see. I pick 0 to 1, 0 minus 1, right? So I pick, so the first half, so we sort this, right? We sort this, and then we have some negative values, some positive values. So basically we divide this array in half, and the first half will go to, basically go to 1, and the second half will go to 0. Oh, wow. Nice. Very nice. Yeah, the same idea as this, but well, that's it. That's it. I don't want to do this. I don't have any capacity left. I want to see if we have more time tomorrow. All right, that will be it for today. I'll see you guys tomorrow. Adios.